Yeah, thank you very much. Okay, so good afternoon, everyone. So, what we did last time, just to quickly remind you, we assumed this theorem and we applied it to solid bricks, right? But this result is about non-removability in bicritical graphs. So, non-removability is very well understood in bipartite graphs, right? We have a very clear understanding of it, and in some sense, this theorem does a similar thing for bicritical graphs. It actually gives us a very strong structure that is then useful in other contexts like solid bricks. So what happened last time is in the applications of this result, we were considering a solid brick, and because the solid brick has no non-trivial separating cuts, we were able to conclude that all the odd components are actually trivial, right? And then basically we had a bipartite graph, but of course there are also even components. And then what we did is we considered two non-removable edges that are adjacent, and then we concluded that in this case there are actually no even components. The two barriers for the two different edges, right? They have only one common vertex, and we were able to get a lot of concrete information in that setting, right? But the result itself that we used is actually for all bicritical graphs with regards to any non-removable edge. Right? So let's see. Let's prove this. So consider the graph G minus F. By the way, in the book they actually said bicritical graph of order 4 or more, but that is unnecessary because bicritical graph by definition has order 4 unless you are Santosh. Right. So so there are times when we allow bicritical graphs to have two vertices, which we do in our paper. But in general, bicritical graphs have 4 or more vertices, and therefore they are non-bipartite. It follows from the definition. Okay, so let us consider the graph G minus F. I think last time I used E for F, doesn't really matter. It is matchable. You deleted one edge and the original graph was not K2, so definitely it is matchable. But it is not matching covered. Therefore it has unmatchable edges. G minus F is matchable. Also connected, although I don't know if you'll use that. I mean, it's probably used implicitly in many places, but has unmatchable edges. Therefore, G minus F has unstable barriers. Yeah, I'm just going to call them unstable, why not? Yeah. In particular, G minus F has unstable barriers. Consider any such maximal barrier. Yeah. In the past, when we were covering ELP theorem, we have discussed Dulmage-Mendelssohn barriers, and one of the results we proved there is that in any matchable graph, every maximal barrier includes a Dulmage-Mendelssohn barrier. We'll make a drawing for that soon. So that was something we proved. So therefore, what we will do is we'll consider a maximal unstable barrier. Yeah. Let B star denote a maximal unstable barrier of G minus F. Then by theorem something in chapter 5, I believe it is theorem 5.4, I'll write down the theorem statement. It includes a Dulmage-Mendelssohn barrier. B star includes as a subset a Dulmage-Mendelssohn barrier. And let me also remind you what a Dulmage-Mendelssohn barrier is. Okay. Here the graph is actually G minus F, right? But I'm refining the Dulmage-Mendelssohn barrier for a matchable graph. The two things we need the core with respect to this barrier. That is of course a bipartite graph. We want it to be matching covered. That's the first property. And the second property we want is that all the odd components are critical. Each odd component of G minus B is critical. And the result we proved back then every maximal barrier of a matchable graph includes a Dulmage-Mendelssohn barrier. And in fact the proof was not too difficult. Well, in retrospect many things are not so difficult. Consider a maximal barrier if it is a Dulmage-Mendelssohn barrier, there is nothing to be done. In particular, if the core is matching covered, then there is nothing to be done because it is maximal. The components are anyways going to be factor critical. Okay. The components are anyways critical because we took a maximal barrier. If the core is matching covered, then we are done. Otherwise, the core is a bipartite graph that is not matching covered, and therefore there is a subset S that basically looks like this. All the edges go like this, and like this in the bipartite graph obtained by shrinking all these odd components. There will be a subset like this, and if the core with respect to B star is not matching covered, then it will be a proper subset of B star, otherwise B is equal to B star. And observe that the odd components of G minus B are actually odd components of G minus B star. Therefore, they are still critical because they were critical anyways. And now because we chose B to be such, we know that the core with respect to B is actually matching covered. Yeah. So we just applied bipartite matching chord graphs theory to this, right? And we got this. Right? So this figure is actually going to be useful even in this proof. Of course, we are going to be interested in applying all of this to G minus F. Right? This is the graph to which we are applying things. Okay. So this was proved earlier and we just discussed it. Questions, concerns, all good? So we are here. since B star is an unstable barrier, the edge F, when I introduce back it into the picture, it must kill the barrier. That's standard stuff, right? Therefore, the edge F, to kill the barrier, its ends must be in distinct odd components of G minus F minus B star. What is clear is that ends of F yeah, so what are the possibilities? Either the ends of F are like this, or like this, or like this, right? Either the two odd components on the right hand side, or the two odd on left hand side, or one on left, one on right. With respect to, now I am looking at B, right? I want to look at this figure. If B is equal to B star, of course, we don't have to do anything. So we are trying to first prove this statement. So, okay, so maybe I should say, we will prove that this fellow B is the desired barrier. Okay, so this is the goal. The goal is to argue that B is the desired barrier. What does that mean? It means that it is a Dulmage-Mendelssohn barrier, that is clear. G minus F has a Dulmage-Mendelssohn barrier, we just took that. So this is fine. We need two properties to hold, the first one and the second one. First, let's consider this fellow. What it's saying is that this case is actually not possible. In fact, this case is also not possible. It has to be this case. Right, there are three cases, 1, 2 and 3. We need to eliminate 2 and 3. DIY. Okay, think about it. Try to eliminate 2 and 3. Yeah.
distance. Yeah.
Suppose it is here. So, nothing also is again here.
Yes.
Which is square. So then this will be.
This will be normal.
So that is what.
And then when you take the code, actually you're removing that, right? Because it is a value in G minus F. So basically what you do is try to see what you can calculate.
So you basically need to consider one case. Consider one case. Take your favorite case. Let's say f is like this. Can you arrive at a contradiction to something in the hypothesis? The question is, what in the hypothesis? Well, there is a barrier. Barriers have something to do with bicriticality. So one natural thing to try to contradict is the bicriticality of the graph. Can you see some contradiction to bicriticality in each of these cases? But just pick one case at a time. And never forget one parity argument. If deleting k vertices gives you k minus 1 odd components, then there is a kth odd component. You don't have to find that component. It is there. Right? So
That's more than these two. There's, I mean, then at least there's dimension. Both are here. The other end is here and B is right. Oh, yeah. Oh, okay. No, I was considering. I think I forgot about this and yeah, that's the only case I was stuck. So now I'm not stuck, I guess. So the other end is in some given component. Then you just include that.
Suppose B is trivial. because one is here and that is also non-trivial barrier. Now if is here, then if you consider okay, for this one. So if you consider B, this is
non-trivial case.
okay.
Non-trivial case are there.
For this type of measurement.
Okay.
For this type of is non-trivial one, 3D and even include mathematics.
Okay, fine. Okay, now consider the other.
I'm considering this yes. Then when you consider this barrier, then the vertical having some even component. It cannot be non-trivial because supposing it is non-trivial. Then the edge will be from here to
In the non-trivial case? No, but we don't know what this looks like. It doesn't have to be one knife. I mean, this one is fine, right?
oh, but this many
That's right. So all of
there.
this is
So this is that even and the F will be like this.
sure. It doesn't work. It doesn't matter what it is.
It is contradicting that.
In this case.
Okay, so I'll give, yeah, go ahead.
It's the same thing again. If it is non-trivial, then this is still if it is trivial, then this will be and then this is the non-trivial element. If it is trivial, then only one odd component.
Now try to do the same thing. No cases. So you did some cases, no? Okay, now use this idea, no case analysis.
Okay, so the point is to contradict the bicriticality of G. And to contradict the bicriticality, one of the easiest ways is to show the existence of a non-trivial barrier. So consider any case, consider this case. Can you spot a non-trivial barrier in G? Yeah, let's erase the other things. Let's erase these possibilities for now. Let's consider this possibility. I claim that there is a non-trivial barrier in G. Right? One easy thing to spot is that if B itself is non-trivial, then you're done, no? If B itself is non-trivial, you're done. Because the odd components of B, if F has no end there, then that continues to be a non-trivial barrier in G. Yeah, so if B itself is non-trivial, you're done. The problem is B need not be non-trivial. Of course, there are multiple ways to argue in this case. That I think Srijit has this point that if this is a single vertex, there is only one odd component, then actually this vertex here is a cut vertex. in this case. In this case, this vertex, single vertex, is a cut vertex. If this is a trivial barrier, if B is trivial, right? That would be a contradiction to bicriticality, well, that would be a contradiction to matching covered and life in general, right? So that is fair, right? But the problem is we are now considering this case, right? So we can, in this case, we got contradiction for everything. Okay, now you can consider this case. Again, you can observe that if B is non-trivial, you are done. Because this kind of edge does not actually kill the barrier B. It kills B star, not B. So therefore, if F looks like this, one end here and one end here, then again, if this is non-trivial, you are done. But you still have to deal with the case where it is trivial, right? But there is one way to kill everything at once. The edge that is bothering you is F. Attack F. If F is bothering you, attack F. Pick an end of F that is convenient. There is an end of F that is actually convenient in both those cases. There is an end of F that I include in B, and I will have a non-trivial barrier in the original graph G. Do you all see that? There is an end of F in both those cases, this case as well as the other case. In both of these cases, there is an end of F that you can include in B. Since you have included in B, now the resulting creature is non-trivial. And the odd components that were originally odd components with respect to B in G minus F minus B, they still are odd components. So you added one more vertex and you got at least as many odd components as before. Therefore, you have one more odd component. You can always include the end of F that is not here. So either this vertex or either of these two vertices. Observe that if you include that end of F in B, then you are done. So if this is the end of F, U, and in this case this is U or this is U, doesn't really matter. Observe that B plus U is a non-trivial barrier in G. Contradiction. G is bicritical. Right? The point is, it's good to do multiple cases, and then eventually you will see that there is actually only one case that takes care of everything. Another way to see all of this is in G minus F minus B, these are the odd components, and everything else here is part of even components. I cannot say there is only one even component, but whatever you see on the right hand side is a bunch of even components. Therefore, I can just take a vertex from the even component, which is something we also did yesterday. We add it to the barrier. Because it is an end of F, it doesn't matter whether you are looking at G or G minus F, right? Because it is an end of F, it doesn't matter. And now you have a barrier. So we actually used a very similar reasoning yesterday, where we took a vertex from an even component, we threw it into the barrier, we say we have a barrier again. This always works in life, right? Okay? Questions, concerns? Yeah? Yeah.
Can you tell that B plus U once more?
Sorry?
B plus U.
My point is, in all these cases, B plus U is a non-trivial barrier in G. These are still going to be odd components. If I delete B plus U in the graph G, because U is an end of F, right? So that contradicts the bicriticality of G. We got a non-trivial barrier. Yeah? Any other questions, concerns? Right? So everybody is okay with this? So what we have done so far is we have proved that this barrier satisfies the first property. It doesn't look like this. The edge F doesn't look like this or that. It actually looks like this. Yeah? This was the first property we wanted. Yeah? Now we need to show this. For every odd component, not of G minus F minus B star, only for these odd components. In fact, it is not true for the other odd components. There is a counterexample shown in Lucchesi-Murthy. Only for these odd components, we will argue that the corresponding cut is a separating cut. Yeah? So in fact this is true, and this implies that ends of F lie in distinct odd components of G minus F minus B, since otherwise B plus U is a non-trivial barrier in G, where U is any end of F that lies in an even component, which means on that side, that lies in an even component of G minus F minus B. That's the argument. Yeah. Okay, so far so good. Now we want to show that each of these is the shore of a separating cut in G. Probably the more standard way of showing that something is the shore of a separating cut or something is a separating cut is to use the other characterization of separating cuts. For every edge there is a perfect matching containing that edge that meets the cut in only one edge. But this time we will do it using the definition of separating cuts. Yeah. So they're equivalent.
Just a minor point. I think it seems like the first property holds true for every DM barrier.
The first property.
That for every DM barrier, the edge F.
Give me a second. Where are we using the DM property? Do you mean for every non-trivial barrier? For any non-trivial barrier of G minus F, if I have a non-trivial, but of course what we did not know is that it is actually non-trivial. Okay. But actually for any barrier, right? It is it. For any barrier of G minus F, let's just do it. If I take any barrier, first let me take a non-trivial barrier. Supposing this is a non-trivial barrier of G minus F. That means there are odd components and even components. If I have a non-trivial barrier in G minus F, let me just write, this is now, we are out of the proof. This is some B prime, non-trivial barrier of G minus F. Okay, since it is a non-trivial barrier in G minus F, but G is bicritical, we must kill this non-trivial barrier. The only way to kill the barrier is for F to look like this. Yeah. The issue is, what if we have a trivial barrier? Then what does it mean? Then it doesn't mean anything, right? Trivial barrier won't give us anything. So that's the thing. Yeah. So in fact, if it is a non-trivial barrier, then you could just prove this little proposition and throw it here. The problem is if it is trivial, then you still need to work. Yeah, and that's actually a good point, because if this is trivial, then this part is actually non-empty, because B star was a non-trivial barrier. So if this fellow is a single vertex, there's only one odd component, there has to be stuff here. B equal to B star is not possible. And we know that the edge F, its other end is in another component, odd or even we don't know. In this situation, we can't say where F is, right? There may be no even components. So the thing that helps here is that if this is trivial, then there are even components, because B is not equal to B star, B is a proper subset of B star, and now we know that F has to go to an even component, and therefore we use that end of F. Yeah. But yeah, in the case of non-trivial barrier, which is what a lot of you observed actually, that if this barrier is non-trivial, then we are just done. At least in the case where F had both ends here, I think most people observed that we don't have to do any work. Right? Of course, what this does is it doesn't care about cases at all. It just kills everything in one shot. Yeah? Okay? YouTube is going to flag me. This guy is using the word kill too many times. Especially in the times of AI where you don't parse anything. Okay, questions, concerns? Alright, so let's get back to our point. So, okay, so what have we done? We took a maximal unstable barrier, right? And then we know that it includes a DM barrier by what we did in chapter 5. So we took that fellow, some DM barrier included in B star, and our goal is to argue that this is the desired barrier. And so far we have, it is a DM barrier anyways, and we also showed this. We are left to show this. For every odd component, we want to show that it is a short of a separating cut. Odd components of G minus F minus B. Right? So let's just write down to show partial of K is a separating cut for each odd component of G minus F minus B. Yeah. Before we do this, let's look at an example where this doesn't happen for an odd component of G minus F minus B star. I'll take this example from Lucchesi-Murthy. They have a nice example. In fact, I want to take a few minutes to spend on examples before we prove this. So here is the example. 1, 2, 3, 4. This is our edge, one more. Okay. This is the graph they have. This is F. This is a bicritical graph. And F is non-removable. That is easy to see because once you remove F, you have a barrier that is unstable. Yeah. This includes a Dulmage-Mendelssohn barrier. Probably this part. Yeah, so they have not shown the B. So basically the point is, this is a maximal unstable barrier, so it fits our proof. We picked a maximal unstable barrier, and what we will do is we will see that there is an odd component that doesn't satisfy the second property. There is an odd component that is not the shore of a separating cut. This is after deleting F, right? So this is a barrier in G minus, this is our B star, this is a maximal unstable barrier in G minus F. And see if you can spot an odd component Yeah. So yeah, in fact there is an odd component here that is not the shore of a separating cut. Most of the odd components are trivial. Clearly they are shores of separating cuts. Let's look at this odd component. One contraction is K4 up to multiple edges. That one is fine. Check the other contraction. Draw the other contraction. Is that matching covered? Let's shrink this, and everything else will keep as it is. F is there. Separating cut in G. Yeah. So we are going to keep F. Is this matching covered? One is not matchable. Which one is it? Which one?
Second from the top.
Second from the top here.
Yeah.
This one?
Yeah, to that dice.
This one? Okay. Let's check. Can anybody find a perfect matching in this edge? No, right?
That also vary.
Hmm?
That
Those two vertices are also barrier. Those two vertices are also barrier. It's unstable barrier. Therefore, the edge causing instability is not matchable. Right? So this is an example that shows that you cannot make this second statement for all odd components of G minus F minus B star. It is important that you look at B, not B star. Yeah? Okay? And basically this B star fellow should not be a Dulmage-Mendelssohn barrier, right? Because if it were a Dulmage-Mendelssohn barrier, then according to the theorem we should actually get, right?
That's probably not true, right? Like the theorem says that there exists solid transform.
No. The way we are proving, we are picking any maximal unstable barrier. Then we are applying theorem 5.4, which says that there exists a Dulmage-Mendelssohn barrier inside this, and then we are showing that this works. Therefore, if B star were equal to B, if B star were a Dulmage-Mendelssohn barrier, then the proof would actually go through. So therefore, this should not be a Dulmage-Mendelssohn barrier. Right? But yeah, that is not because of the theorem, that is because of the way we are proving it. Yeah. So in fact, we can make this stronger. We can say that consider any maximal barrier that is unstable and it contains a Dulmage-Mendelssohn barrier which could be equal to itself for all we know, and this fellow has the properties we want, which is actually what we are proving. We are proving a stronger statement. Yeah, good. Okay. Any other questions, concerns? So far so good?
Is it similar to say any DM barrier in that?
No. Any DM barrier inside a maximal unstable barrier. Then it is fine. That is what we are actually proving. Yeah. The reason this is interesting is because of last time's example. Let's draw the example from last time. We considered the Murthy graph, and there was a point where we all were confused slightly. This is F that we considered last time. 0, 1, 2, 3, 4, 5, 6, 7. And there was a point where we were considering, after deleting F, let me erase F. After deleting F, we were considering a particular barrier. If I am not mistaken, we were looking at 2, 4. Observe that 2, 4 is a barrier in G minus F. Is it maximal, by the way? That I did not check.
Yeah.
Is it maximal?
The two components are factor critical.
The two components are factor critical. If it were maximal, then the two components should be factor critical. And is the converse also true? Is it true that if the components are factor critical implies the barrier is maximal?
Otherwise, there will be some other set of vertices within a component which you can include to the barrier.
Yeah, I think you're right. Yeah. Yeah. So it looks like, check carefully again. It looks like 2, 4 is a maximal barrier in G minus F. But this is really not a good barrier for anything we are trying to do. First of all, is it a Dulmage-Mendelssohn barrier? Well, it is a maximal barrier. It should include a Dulmage-Mendelssohn barrier. Is it itself a Dulmage-Mendelssohn barrier?
Yeah.
It is a
It is a Dulmage-Mendelssohn barrier, yes, because you get C4 or something, I guess. But observe that this is not true. Observe that for the two odd components, Neither of them is the shore of a separating cut in G. G is in fact solid. That should not have any non-trivial separating cuts. Both the odd components are non-trivial. Their complements are also non-trivial, well, because they are both non-trivial. Right? Observe that neither of these is the shore of a non-trivial separating cut. Right? So this barrier would not have worked, and the reason it doesn't work is because we took a barrier that is not unstable. Observe that 2,4 is not unstable, it is actually stable. Right? That is why the proof is not really, there is no problem with the proof because of this example. Right? The proof starts as an unstable barrier. Right? So, yeah. Okay. Questions, concerns? All good? Okay. So these are all good examples that make us appreciate what we are hoping to prove. Sorry? Let's stop recording?
10% battery.
Okay. Shall we? I'm thinking of taking a break anyways and proving after the break. Yeah, so shall we take a break here? We have more battery. Okay, thank you.